Continue with another example problem. In this example problem, air enters a nozzle steadily at 280 kilopascals and 77 degrees Celsius with a velocity of 50 meters per second and exits at 85 kilopascals and 320 meters per second. The heat losses from the nozzle to the surrounding medium at 20 C are estimated to be 3.2 kilojoules per kilogram. Determine the exit temperature and the total entropy change. So let's start with a schematic. We have here a nozzle with air, and we have air coming in at the first state and exiting at the second state. Where the first state we have the pressure is 280 kilopascals, temperature is 77 degrees Celsius, and the velocity is 50 meters per second. And then exiting, we have a pressure of 85 kilopascals and a velocity of 320 meters per second. We're going to go under the assumption that we have an ideal gas. And like always, when we have an ideal gas, we have to assume variable or constant specific heats. In this case, we're going to assume variable specific heats. And then we're going to assume this problem to occur at steady flow. So what we're asked to find is the exit temperature and the total entropy change for the process. Now, it's telling us too that there's heat loss to the surroundings at 3.2 kilojoules per kilogram. So, first step would be to do a first law analysis. If you remember a first law analysis, this is a steady flow problem, right? So we have E in minus E out equals delta E system. This is a steady flow problem, so delta E system is 0. E in equals E out. That means energy in by heat, mass, and work equals energy out by heat, mass, and work. So we have mass energy going in. It's carrying in with it enthalpy and kinetic energy. We have mass energy going out. Actually going in, we'll call this H1 and V1. Going out, we also have mass going out, carrying out enthalpy at 2 and kinetic energy. And then we have heat going out. Now in this particular problem, everything is left in terms of specific units. So if I divide through by mass, I get H1 plus V1 squared over 2 equals H2 plus V2 squared over 2 plus heat per mass leaving. Now, for this particular problem, it's asking us to determine the exit temperature. Now, if you recall, enthalpy is a function of temperature only for an ideal gas. So if we go ahead for this problem and we solve for H2, we could rearrange our equation into the following form. Keeping in mind to multiply the kinetic energy by 1 kilojoule per kilogram over 1,000 meters squared per second squared. Now, I have Q out. I can get H1 from the ideal gas tables in the book. So if you go ahead and you take your books and you turn it back to table A17, which is the ideal gas table for air, you can go ahead and you can find for a temperature T1 of 77 degrees Celsius, which converted into Kelvin would be 350 degrees or 350 Kelvin. You would go to table, so at table A17, you would go ahead and interpolate for the enthalpy, which would be 350.49 kilojoules per kilogram. So in that case, you can use this equation and solve for H2, and you would get a value of 297.3 kilojoules per kilogram. And then from table A17, you can go ahead and interpolate for the temperature, and you would get a temperature of 297.3 Kelvin. Part B is asking you to find the change in enthalpy, or I'm sorry, the change in entropy of the ideal of air. So you would find, or I'm sorry, it wasn't a change in entropy of the air. It's the total change in entropy for the process, right? So that would be equal to the change in entropy for the air plus the change in entropy to the surroundings. Now, it so happens that the change in entropy for the air will be the change in entropy for an ideal gas with variable specific heats. So that would be S20 minus S10 minus R natural log P2 over P1, since that is the equation for calculating the change in entropy of an ideal gas with variable specific heats. So you can go back to your ideal gas tables, right? So you turn back to table A17 in your book, and then once you get there, you find for a temperature of 350 Kelvin, you would find that the entropy, temperature-based entropy, the S0, would be 1.85708. And again, that is kilojoules per kilogram Kelvin. You would find that for S2, it would be 1.6924 kilojoules per kilogram Kelvin. So at this point, you have all your nodes. You have P1, you have P2, you have S20 and S10. You can plug in your numbers, and you would get a total entropy change of just the ideal gas of 0.1775 kilojoules per kilogram Kelvin. Then you can go ahead and you can find the entropy change of the surroundings. Now, the entropy change of the surroundings is due only to the fact that you have heat being added to the surroundings coming from or going into the source, right? So, I'm sorry, going to the sink. So you would basically take the heat transfer, 3.2 kilojoules per kilogram. That is the heat transfer per kilogram or per mass of heat being lost by the nozzle, divided by the temperature of the surroundings, which in this case is 20 C, so that'll be divided by 293 Kelvin, and you would get that the entropy change of the surroundings due to heat transfer to the surroundings, or entropy transfer by heat, is 0.0109 kilojoules per kilogram Kelvin. And then you would add those two numbers together to get the total entropy change for the whole process, and you would find out it is 0.1884 kilojoules per kilogram Kelvin.